Welcome back. Today we're going to be looking at probability. A lot of this is most likely, a lot of this is probably going to be very, very familiar to you because probability is something we've done, and most of what we're going to be looking at right here is not horribly difficult. Again, it's probably stuff you've already done, but want to make sure everyone's on the same page with everything. We're going to get some vocab. The vocab is important, as always, because when you're asked a question on a test, you need to know what it means in order to be able to answer that question. So, we're going to be looking at theoretical and experimental probability, plus a few other little things in there. Our learning targets for today: I can find the theoretical probability of an event, and, wait for it, I can find the experimental probability of an event. I mean, really, these learning targets are just jaw-dropping. So, let's look at probability in general first. Some vocab before we get started. We have sample space. Now, the sample space is anything that can happen. It's a set of all possible things that could happen. I want to say it's a set of all possible outcomes, but outcome is the next vocab word. So anything that could possibly happen. Generally speaking, it is signified by a capital S, and then it's a set. So we use set notation. It uses the big squiggly brackets, and we just list everything that could happen on the inside. Example, if I roll a dice, the sample space is 1, 2, 3, 4, 5, or 6. Those are the possible things I could get. If I flip 2 coins, the sample space, I could get heads and head and tail and head, and tail and tail. So those are the 4 possible things from flipping 2 coins. So that's the sample space. Notice it's not always numbers. It could be letters, could be words. We'll see more sample spaces as we go. So the next one is an outcome. And an outcome is just a piece of the sample space. One thing that could happen. An element of the sample space. Element just means it's a piece of it. Example, outcomes. Roll a dice, get a 2. Flip 2 coins, get 2 tails. Like any one of these things is an outcome. What if we want to include more than one thing? That's called an event. An event is a set of possible outcomes, or a subset of the sample space. Examples of some events: we could roll an odd, a 1, 3, or 5. We could get at least one tail, so we could get head tail, tail head, or tail tail. We could roll a 2 or a 3. It could just be one outcome. We could roll a 6. That is an event. It just doesn't have to be only one thing. And so, for a formula, in general, probability is success divided by the total. That's how we do probability. And we're going to see a couple different types of probability where the equations will be slightly different, but it's just a different way of looking at it. It's still going to be success over total. The notation for probability, we have a capital P, and then it's probability notation, or function notation. Probability of rolling a 1, 2, or 4. Now with function notation, we would have to plug rolling a 1, 2, or 4 into all of our variables. Not so much with probabilities. It's just the probability of rolling a 1, 2, and 4. You can shorten that if you would like to. Chances are at this point we'd be thinking about dice anyway for this problem. So just P 1, 2, 4. But you can also write out a full sentence if you would like. It doesn't matter. And it doesn't have to list the events. It could be or list the outcomes. It could just be the event. Probability of rolling an odd. Based on our previous knowledge, we know an odd would be a 1, 3, or 5. And it could be quite a bit longer. could be probability of flipping 2 coins and getting 1 head and 1 tail. Chances are, if you had a problem like this, you know that you're flipping 2 coins. So it'd probably just be P of 1H and 1T. But again, you can be more verbose. If brevity is not your thing, feel free to let it all out here. And so, as we're talking about rolling dice, talking about these guys, we have different names for these. The book calls these things number cubes because dice implies gambling. Me, I call them dice because number cubes is stupid. So we're just going to call them dice. But when you see a question in the book and it says you roll 2 number cubes, it means dice. Now, you notice I have it capitalized. It's because while I like the thing, and seriously, in statistics, I can't teach you how to play craps using number cubes, so we're going to use dice. But you can notice it's all in caps. That's because I'm not a huge fan of the singular form. Dice is plural. It's more than one dice. It's one die. And it's just awkward using it in a sentence. So I made it an acronym, and dice would be dotted integral cubic experimenters. And so that way I can use it as singular or plural, and it doesn't matter. So every time I type it, you will notice that it is all in caps, and that's why. So, from here, things about probability. The probability of any event is always going to be between 0 and 1. 0 is the smallest thing it could be, 1 is the biggest. I know a lot of people try and say, well, it's 0 to 100. No, that's a percent. There are small differences, nothing hugely important, but probabilities go between 0 and 1. 0.5 is, for all intents and purposes, equivalent to 50%, but the probability is 0.5, not 50. If we look at those endpoints, if the probability of an event equals 0, what does that mean? That's most likely right, whatever you just said. It means that event E cannot happen. It will not happen. Never, ever. It just can't. For example, I roll 1 dice. What's the probability of me rolling a 7? 0. 7 is not one of my options. It is not in the sample space. So, that's what probability equals 0 is. If the probability of an event equals 1, it's exactly the opposite. It will always happen. For example, if I roll 1 dice, I will get a number between 1 and 6. I will always get a number. And so, that would be a 1. The probability of the sample space always equals 1. And so, that's some stuff on probability. Now let's look at some specific types. Theoretical probability is the first one we'll look at. And I am fairly certain every single one of you has done theoretical probability before. Theoretical probability can be thought of as, in theory, this will happen. For example, if you roll a dice, what is the probability of rolling a 2? You probably just said, that's 1/6. There's 1 2 out of 6 sides. Yes, that is theoretical probability. Our formula for this, it's the number of successes divided by the total number in the sample space. So, remember, probability is success over total. Here it's the number of ways to get successes divided by the total number of outcomes in the sample space. So, let's say we roll a dice. What's the probability of getting a 2 or a 3? How many ways could we successfully get a 2 or a 3? That'll be 2 ways. We can get a 2 or we can get a 3. It's 2 divided by The total number of things that could happen, 6. So the probability is just 2/6, which, yes, that does reduce to 1/3, and you can feel free to do so. How about we have a bag of marbles with 3 red, 5 blue, and 2 green marbles in it. You pick 1 marble. We'll have a few marble questions, partly because it's really easy to write a problem involving this, what doesn't always have 6 in the denominator, or flipping coins is always the same. You can change up the number of marbles, how many colors of marbles are in the bag, things like that. So it's really easy to write a problem. Also, I thought I had lost my marbles, but I just recently found them, so I'm kind of excited about this. So we have a bag of marbles, 3 red, 5 blue, 2 green. You pick 1 marble. First of all, the sample space. The sample space here is, if you pick 1 marble, what are the possible things that could happen? You could get a red, a blue, or a green. So the sample space would just be red, comma blue, comma green. We don't need to repeat the colors a whole bunch of times. It's just red, blue, green. Because if you draw a marble, those are the things that could happen. All of those things are not created equally, however. So we pick 1 marble. What is the probability that it's red? What do you think? Well, there's 3 reds out of 10 marbles. 3/10. Yes, this is theoretical probability, and we're actually spending time looking at this. How about we get a red or a blue? Well, there's 3 reds and 5 blues, so number of ways we could succeed, 8/10. Now let's look at a deck of cards. Now, a deck of cards is something that comes up. There's some background knowledge here that I expect you to have, but in my experience, not everybody does coming in. So let's explain a deck of cards really quick. First of all, there's 52 cards in this deck. They're split up into 4 groups called suits. There's hearts and diamonds, which are both red. There's spades and clubs, which are both black. So if it's looking for a red card, half of them are red, half of them are black. Each suit has 13 cards, a 1 through 10. 1 is also known as an ace, and then a jack, queen, and king. The jack, queen, and king are known as face cards because they have a face on the card, whereas the rest of them have numbers. So if you're looking for what's the probability of a face card, there's 3 out of 13. And then since each suit has exactly 1 type of card, and there's 4 suits, there are exactly 4 of each kind of card in the deck. Example, there's 4 aces, 4 twos, 4 threes, 4 kings, things like that. I can answer some questions. Generally speaking, by the time we get to any kind of test or quiz, even people who claim to have known nothing about a deck of cards knows enough to be able to handle any of these questions. But if you do have a question on them, feel free to ask. And so, we have our deck of cards, and we're going to draw 4 cards from this deck. And in the 4 cards, we want, what are the probability that we draw? What's the probability we draw all 4 aces out of those 4 cards? And so, here's where what we were doing yesterday comes in, with counting. How many ways are there of drawing the 4 aces? And then how many ways are there of drawing 4 cards? And so, we'll get our fraction. How many ways are there of drawing the first ace? Well, there's 4 of them in the deck, so there's 4 ways. And then the second one, now there's only 3 of them. And then the third one, there's only 2. And then there's 1. So to draw 4 aces, there's 4 times 3 times 2 times 1. 24 ways that we could draw those 4 aces. And that would be hearts, then spades, then clubs, then diamonds, or hearts, then diamonds, and spades, then clubs. Rearranging them, we get 24. And then how many ways can we just draw 4 cards? Well, how many ways are there of drawing the first card? 52. And the second card, there's only 51. And the third card, 50. and the fourth card, 49. So if we multiply those together, we're going to get 24 over 6,497,400. I used a calculator for that. I did not do that in my head. And then we can reduce the fraction. So the probability of drawing 4 aces is 1 over 270,725. I wouldn't recommend putting that as a decimal because it's going to be a really small decimal. I would leave that as a fraction. And so that's a probability of drawing 4 aces. What if we wanted the probability of at most 3 aces? So that means we will have at least one card that is not an ace. We could go through and figure out every single possible combination, but that would take a lot of time. And so, instead, we're going to look at it in another way. And that is, we're going to need another vocab word, and we're going to look at the complement. Now, a complement of a probability is when one probability says something nice about another probability. Wait. No, that's not right. Spelling. The complement. Spelling is important, people. The complement of an event is the event that event does not occur. Isn't that a great definition? The event that the event does not occur. It doesn't happen. So rolling a 2, the complement of rolling a 2 is not rolling a 2. The notation for a complement of event A is A, and then it gets a C for complement as an exponent. It's not actually an exponent, it's just where we put the notation. So the event, if event A is rolling a 2, AC is not rolling a 2. So we could get a 1, 3, 4, 5, or 6. In our case, if event A is drawing 4 aces, A of the complement is not drawing 4 aces, which means we have at least one other card. We have at most 3 aces. So how are we going to use the complement to help us here? Well, the nice thing, let's look at rolling a 2. If we roll a 2, or we don't roll a 2, is there anything else that could possibly happen? No. An event and its complement covers the entire sample space. And so, what is the probability of the sample space? It's 1. So the probability of an event plus the probability of its complement equals 1, which means we can also subtract the probability of a complement equals 1 minus the probability of the event. So not drawing 4 aces, it's going to be 1 minus the probability of drawing 4 aces, which we already found, and that one wasn't all that hard to find because there's really only one way of doing it. We can't mix other cards in there. And so it's 1 minus this number. Well, we can make common denominators. 1 is going to be 270,725 over 270,725 minus 1 over that gives us 270,724 over 207,725. So if we were to list out all the events, we would have to list out all 270,724 possibilities, and that does not sound like a good time. Using the complement was much, much easier. And so, again, that's theoretical probability. In theory, what's going to happen. Next one, geometric probability. Here, and this is actually just a type of theoretical probability. We're going to use shapes, though. Because if you have shapes, you don't really have the number of successes and the total number. That doesn't really make sense. So instead of numbers, we're going to use the area. It's going to be the area of success divided by the total area. Something here, we could have a target. So we have a target with this distance is 4, and the distance here is 5, and the distance here is 3. we can find the probability of hitting a bullseye, getting it in the red circle. So it's going to be the area of success. That's going to be the area of the red circle divided by the total area is the area of the whole big circle. So if I throw a dart at random, assuming I have absolutely no skill in throwing darts, which is a fairly safe assumption, what's the probability I get a bullseye? So we have the area of the red divided by total area. The area of the red, it's just the area of a circle. We have pi r squared. R is 4. So pi times 4 squared. And then the total area, and this is where people mess up, because they say, oh, it's pi times 3 squared. Is 3 the radius of this big circle? No. We have to add these together. That's really the way that they can trick you on this type of problem. 4 plus 5 is 9, plus 3 is 12. So we have pi times 12 squared for the big area. Now, one of the cool things about these problems, notice we have pi times something over pi times something. The pi's cancel. So really, we just have 4 squared, which is 16, over 12 squared, which is 144. And then we can reduce. To get the probability of hitting the red circle is 1 over 9. Right? So one way they try and trick you up a little bit is by not giving you the actual radii, but just giving you the distance of the rings. The other way that this type of problem could be a little bit more challenging is the probability of the green circle. It's going to be the area of the green circle divided by the total area. And so the green circle, some people are like, well, the green, that's just pi times 5 squared. No, areas don't work like that. To find the area of this green ring, we're going to have to find this total circle area minus this piece inside. And so we'll have pi times 9 squared minus pi times 4 squared. And that will find this green area here. And then the total is still pi times 12 squared. The pi's still cancel because everything has a pi in it. And so really we just have 9 squared minus 4 squared, which is 81 minus 16 over 144, which is 65 over 144. That's the probability of hitting it in this green ring. Sorry, there's a pause here because I'm trying. There's something I just wanted to mention. I'm trying to think of it. It's not there. No, nothing. I just had it. It was just in my head. Gah. Let's see, total area, area of green, area of red, total area, blah, blah, blah. Oh, I remember now. So, back to the red circle. Right, this is in the center. What would happen if the circles just kind of stay the same, but I took the red circle and I moved it up here? Would that change the area? What if I moved it so it was even covering both green and blue, but still staying inside this big circle? That will not change the probability because the area of the red circle is staying the same and the total area is staying the same. So it doesn't matter that it's in the inside. Hitting this circle would be the same as hitting a circle with radius 4 right over here, which would be the same as hitting a circle with radius 4 right over here. That probability does not change if we move the target. So, the third type of probability we're looking at is experimental probability. And this is similar to theoretical probability, except instead of based on in theory, it's based on an experiment. And the probability, it's going to be the number of successful trials divided by the total number of trials. And a trial is another vocab word here, and it's just when you do things. For example, I pick a bunch of marbles out of a bag. Each time I pick a marble, it's a trial. I roll the dice a bunch of times. Each time I roll the dice, it's a trial. I flip a coin a bunch of times. Each time I flip a coin, it's a trial. And so that's the vocab word for here. And so, experimental probability, we have a bag of marbles. We don't know what's in the bag, but I draw 15 marbles, one at a time, always putting it back. That's a with replacement thing. That way, each time the probability is the same. If I kept the marbles, the bag is changing. It's changing the probability of the bag. Anyway, so I do this 15 times, and I get the following results. I got blue twice, I got red 5 times, green 4 times, and orange 4 times. And so we can find some probabilities. We can find the probability of blue, probability of red or orange, and the probability of it not being green. So if I draw another marble out of the bag, what's the probability that it's going to be blue based on our experiment? You think you have it? Well, how many times do we get blue? 2. That would be the number of successful trials, because in this case, blue would be a success, divided by the total number. I drew 15 times, 2/15. What's the probability of getting a red or an orange? Well, let's see. I was successful there 5 plus 4, 9 times out of the 15. It's 9/15, which does reduce to 3/5. And then how about a probability of getting not green? How many ways could I get not green? Well, we could count 2, 7, 11, or we know there's 15, wasn't 4, so subtract, that's 1. That was using the complement. Not much of a difference here. Either way, we get 11 out of 15. That's experimental probability. Very, very similar to theoretical, especially in a problem like this. The type that trip people up is, I roll a dice 25 times and get the following results. I get 1 3 times. I get 2 5 times, 3 4 times, 4 I rolled 7 times. I didn't roll a 5, and then I rolled 6 times. And you might think, well, I don't know why this is going to trip us up. Well, we get the probability of rolling a 2, get the probability of rolling a 3 or a 4, and the probability of rolling a 5. So what is the experimental probability of rolling a 2? It's not 1/6. That's theoretical. How many times do we roll a 2? 5. Over how many times do we roll in total? 25. And so we have 5 over 25, which reduces to 1/5. How about the probability of rolling a 3 or 4? All right, so a 3 or 4, that's 4 plus 7, that's going to be 11 over 25. Now, people usually get those. What's the probability of rolling a 5? This is the one that gets people so often. Because you ask the question, it's like, well, it's 1/6. It's not. The probability of rolling a 5 is 0. It happens 0 times out of our 25 rolls. Does that mean it's actually impossible to roll a 5? No. But in our experiment, for our experimental probability, the probability of rolling a 5 is 0. Experimental probability, one of the things it could be used for is to figure out if the dice are loaded or not. Are they going to be evenly distributed? Based on what we have, it looks like no. But we only rolled it 25 times. If we really wanted to figure out if this was loaded, we'd have to roll it at least 1,000 times and see if we're getting about the same number each time. If at that point you hadn't gotten a 5, I'd say it's fairly likely that it would be impossible to roll a 5 on this particular dice. But experimental probability is based on the experiment. It doesn't matter what you know about situations outside of the experiment. It's only the experiment, and this one in particular is what trips people up, because of course you can roll a 5. Maybe. We don't know. And so that's experimental probability. One last little recap. We have three types of probability: theoretical, geometric, and experimental. I just really want to get these all on one page. So theoretical probabilities, in theory, what's going to happen? It's the number of successes divided by the total number of things in the sample space. Geometric probabilities on shapes and area. It's the area of success divided by total area. And the experimental is based on experiment. It's the number of successful trials divided by the total number. So do you see how probability, it's always success over total, success over total, success over total? It's just, how would we describe the successes? And that's the difference between the formulas. Because if we just use geometric, the area, that would not make sense for the other two. And again, the other two wouldn't make sense for any of the others. So that's why we use slightly different terminology. Anyway, hopefully you learned something. But again, this is probably a lot of review, but that's okay. It's nice to have a little bit of review once in a while. Hopefully you were entertained slightly, and I will see you in class.